forces that we have to consider. The first one is the pressure, inside the capillary. This pressure favors things to leave the capillary. It favors filtration, okay? Because there's blood in here that's pressing on the walls of the capillaries. We have another force that opposes this one. It's the opposite. It's the pressure of the interstitium. And it wants to push fluid or water back into this vessel. Okay, those are two of the forces. We got two more. Then we have the colloid osmotic pull of the interstitium. It means that there's stuff out here like cells or solutes or proteins or bacteria or something. There's stuff out here that pulls water by osmosis. So this force, this oncotic, osmotic, all synonyms, this pressure is pulling water out. Okay, so it favors filtration. We have an opposing force because there's stuff like proteins, blood cells, so on and so forth in here. And it's pulling water in. So we balance these four. If overall we have a positive number, that means that we'll have filtration. If we have a negative number, it means you have absorption. So the net driving force equation ends up being pressure in the capillary minus pressure of the interstitium minus osmotic pull into the capillary minus osmotic pull into the interstitium. And that gives us our number, okay? Let's break this down a little bit. What is responsible for this force? What is responsible for P of C? What causes that to be a real thing that happens?
Circulation.
Circulation, right? What else? What's in the capillaries? Blood pressure. There you go. The reason this exists is because there's blood pressure in the vessels. Right? Why does this exist? Why is there pressure in the interstitium? Is there stuff in the interstitium? Are there cells? Are there tissues? There are things in an enclosed space. There's pressure. Why? Because there's stuff in the interstitium. Okay? What about this pressure, or this osmotic pull? This is the one that's pulling in. What is responsible for that?
Solids in the blood.
Solids in the blood. What's the biggest solid in the blood? Biggest one? Plasma proteins. Right on. What about this one?
Solids in the tissue.
Solids in the tissue. Okay, we got that. Okay, that's one idea that we had to talk about. Let's talk about edema. What's edema?
Fluid in the interstitial space.
Fluid in the interstitial space, exactly. So, what can cause fluid to accumulate?
Blockage in the.
Okay. Lymph block. What else? What can we do to these forces?
Filtration.
Filtration, okay. How can we increase filtration? Let's think about a way we could increase filtration.
You get a hemorrhage.
I'm sorry, Queen, I didn't hear you. Did you say anything? Oh, sorry. Okay. We want to but you changed your mind.
I did my mind.
Okay. We want to increase filtration. What's a way we could increase filtration?
Chris said there was hemorrhage.
Sorry, what?
She said there was a hemorrhage.
Why are you selling out your classmate? It's because she teases you, right?
Yes.
So, you're getting back at her. Okay.
No problem.
She got it. She got it. It's okay. You're right most of the time, so consider that. Okay. Okay. We want to increase filtration. What would happen if we made the capillary more porous? We put holes in the capillary wall. Would it be easier for filtration to occur?
Mm-hmm.
Okay. So.
But wouldn't that
capillary-
also be easier for absorption?
Would it be also easier for absorption? Yes. So then we would have to do two things. Not only will we have to make the capillary porous, but we would have to increase one of the pressures. Which one?
To increase filtration, you'd have to increase the,
Hydrostatic pressure.
Hydrostatic pressure. We would have to increase pressure in the capillary. How can we do that?
Okay.
Increase blood pressure. Okay. What about these two guys? What would lead to more edema? How could we make this pull of water into the capillary less?
By increasing caustic osmotic.
Out here, okay, yeah, that's one way we could increase here. What about if we just thought about this one? How could we decrease this force?
dehydration.
No, that would increase the force. If this vessel was dehydrated,
Yeah.
it would pull even more water
I
in.
was thinking dehydration in the muscle, but
If we decrease
What about-
plasma
What about these guys? What could we do to plasma proteins so that there's less of a pull into the blood vessel?
decrease.
Decrease, right? So decreased plasma proteins. All of these things are going to lead to edema, okay, or an increase in fluid in the interstitium. Okay, that's one idea that we need for the quiz. What else we got? Let's talk about different kinds of capillaries. We have 5 kinds. Anyone? Start listening.
Artery.
Continuous, specialized, continuous, fenestrated, sinusoidal. Okay. Were there only 4 or am I just special? There were 4. Okay, I thought there were 5. Where are these guys? Everywhere. These guys are everywhere, except for cartilage.
Epithelium.
Where are these? Specialized, continuous.
How about epithelium?
The epithelium, yeah, also no cartilage, no epithelium. Okay, what about the specialized continuous? Remember, the only difference between these and these are these have tight junctions between the endothelial cells. So where would the specialized continuous be?
CNS and thymus. Specialized.
Specialized, blood, brain, barrier. Okay? Don't want anything to get through them. These are already the smallest ones. Now we're making them small and tight. Very, very little things can get through there. What about the fenestrated ones?
Where do we find them?
Yeah,
Bone marrow.
no. That's the sinusoidal ones.
Liver?
That's also sinusoidals. It's liver. We got sinusoidal.
Okay.
Okay.
We'll skip that one. We'll come back to it.
Coron
Liver,
plexus.
spleen, bone marrow.
Coron
Kidneys,
plexus. Coron plexus.
Choroid plexus, yes. Also, glands. Endocrine glands. Right? Because those places make hormones that we want to put into the bloodstream. So we need a bloodstream with lots of windows. Or the fenestrated capillaries. Okay, got that. What about, let's see, what about where is blood? Where is blood in your body?
veins and arteries all through the body,
Veins and arteries all throughout the body. Where's the majority of blood?
in the veins.
Veins.
Veins, right? 60% of blood is in the veins. 40% is in arteries, heart, and capillaries. Okay? What is venoconstriction?
Constriction of the veins.
Constriction of the veins, exactly. What would happen if venoconstriction happened? We constricted the veins, made them smaller. Where would blood go?
Towards the arteries.
We'll have more.
You put more heart, arteries, and capillaries, right? Okay, good job. What else we got? What are things that you guys remember about total peripheral resistance? we'll put it here. I know it's becoming a mess. Total peripheral resistance. What are things that we said contributed to that?
Turbulence.
Diameter. Right? How does diameter relate to the resistance? Do you guys remember? How does radius?
Smaller, the more resistance.
The smaller, the more resistance, right? And that relationship was radius to the fourth power is equal to the inverse of resistance. So when radius goes up, resistance goes down, and vice versa. When radius goes down, resistance goes up to the fourth power. Okay? They're an inverse relationship. Okay, so radius or diameter, that's one factor. What's another?
Wait a minute. When radius goes up, the resistance goes down? Okay, yes.
Because you.
Yes.
Valves.
Valves? No. Resistance. There was a list of things that we said about resistance. There was a whole equation. It looked something like over 4 on
The length of the vessel.
length. Okay? Length of the vessel matters. It's constant in adults, but it's still a term that we have to talk about. What else? We're going to have 1, 2, we'll have 2 more.
Blockage.
Blockage. What's another way we can think of it? Are you talking about like atherosclerosis, where you have a blood vessel, and then all of a sudden there's something here on the sides? So what happens?
Turbulence.
Right? We had laminar flow, and then it became turbulent. Right? Turbulence.
Yeah, that's
Right on.
Viscosity.
Viscosity. Perfect. How viscous the blood is. Okay, all of these things are related to resistance. That's how we figure out resistance. Okay, that's good. What else we got? Got that one? Okay, while we're talking about resistance, what are the resistance vessels in the body? What are the vessels?
Capillaries?
No. Well, how would capillaries are made? What is the state of their tunica externa, media, intima in a capillary?
In a capillary, it doesn't have media and externa.
Exactly. It's only the interna. It's just an endothelial cell. So how could we constrict an endothelial cell without any smooth muscle? Okay, so total peripheral resistance by capillaries? No. What about venules? Do venules have a lot of smooth muscle, comparatively? No, not really. What about veins?
Yes.
Yes.
Veins have smooth muscle, but do we constrict veins often, or do we only do it to get to venous reserve? We don't do venoconstriction often. We're talking about peripheral resistance is vasoconstriction. So venules and veins, no, they're not really responsible for, we're looking for resistance vessels. These are the vessels, arterioles. Why?
They have muscle to.
Because they contract at each heartbeat.
Because they contract at each heartbeat, because they're small, because there's so many of them. Arterioles are the resistance vessels. Arteries are conducting blood to an arm. You are not going to take this artery in the arm and constrict it. That's not going to do anything. We're not going to constrict it. We're going to constrict all of the little vessels leading into capillary beds. Okay, arterioles. It wouldn't make sense to constrict them. That wouldn't increase peripheral resistance, right? Where did we see the greatest cross-sectional area? If you compared arteries to arterioles, what has more cross-sectional area? Arterioles, because there are more of them, even though they're smaller. Okay, so arterioles are the resistance vessels. What are our capacitance vessels? What is capacity?
It can hold blood.
Can hold a lot.
Veins.
Veins are called capacitance vessels. Cool. Let's see what else we got. You guys are going to get to this quiz and be like, this is so easy. Okay, blood into the heart equals what? Blood in equals blood
Out.
out. So what's another way of saying that?
Cardiac output.
Cardiac output equals venous return, right? Blood into the heart equals blood out. Got that? Okay, we got one more thing to talk about and then we're done. Our good friend, our good equation, the change in blood pressure equals flow times
Resistance.
cardiac output, or flow, or milliliters per minute, times resistance, right? What would happen if I took this term and I multiplied it by 4? What would happen to this number?
Increase.
It would increase by how many?
4.
By 4, okay? If you don't believe me, let's try it. Let's say that our cardiac output is 5, and that our resistance is 2, and that would make our change in blood pressure 10. Okay? So we get 10 equals 5 times 2. All right, we're going to take this 10 and multiply it by 4. So now it equals 40. And we say x times 2. 40 divided by 2, x equals 20. 20, originally it was 5 times 4. Okay? If you're ever unsure, pick some random numbers, pick low numbers, don't try to do 120, okay? That's going to mess you up. Pick some 1, 2, 4, pick some easy numbers, plug them in, see what happens. Okay? You're good, you're ready. You're going to get 100 on the quiz.
Thank you.
You're welcome. Go share some knowledge.